Hi, I'm Anaïs Artiges, and I will present Ginkgo, a novel modular and open source MRI pull sequence development framework. As you may know, when you want to develop MRI pull sequences, you will need a development kit from your MRI manufacturer. But this can come with some limitations regarding intellectual property, access to particular codes, or difficulties to read the code that may be very well embedded in the manufacturer's source code. We thought that an open source project will provide accessibility in the participative environment that could be cross-manufacturer for MRI pull sequence development, as Gadgetrun is for MRI reconstruction. Here you can see a class diagram of the Ginkgo framework. It has been built using an object-oriented architecture based on factories. The sequence module factory is generating different sequence modules, which have an anchor time and a duration, allowing us to place them on the sequence timing. Deriving from this sequence module, you will find preparation, excitation, refocusing, readout, and spoiling modules, which are the basic modules to build any MRI pull sequence. Deriving from them, you will find more specific modules, allowing you to build different MRI pull sequences. For instance, if we want to build a spin-echo 3D EPI sequence, you may need some preparation modules like fact saturation or diffusion weighting, but you will need 4 main modules. The single TX excitation 3D module, shown in blue, the refocusing 3D module in orange, the ecoplanar reading 3D module in green, and the spoiling 3D module in purple. If we dive into the code, you will find 4 main methods. The initialize method, setting the default parameters of the sequence. The prepare method, setting the different events of the sequence, like the gradients, the radiofrequency pulses, and the ADC events. The run kernel method, putting them all together in one timing, like for run 1 repetition time. And the run method, looping over lines, slices, partitions, repetitions, and even diffusion orientations. If we look at figure 1, which is the constructor of a spin-echo 3D sequence, you will need to call the sequence module factory and to say the module's name each time you want to call a module. Here we will need a single TX excitation 3D module, a Ginkgo refocusing module, a single line reading 3D module, and the spoiling module. The end module is just to go until the repetition time is attained. Sometimes the modules will need you to define some background parameters like the single TX excitation 3D module. Once all the modules are called in the constructor, you will be able to use them in the other methods. For instance, in the run kernel method, you will find the place where you set the anchor times. You will need to set the anchor times of every module before running their inner methods. After the run kernel is set, you will be able to modify your run method and set it on the loops that you need. For instance, here we want to build a spin-echo 3D sequence, so we will need maybe a loop on repetitions, but mainly loops on lines and partitions. If you want to implement the Ginkgo framework, you will need to download it from the Framagit repository and copy-paste it on your IDEA-sec file. You can then directly compile the DLL and SO files using the completed sequence proposed in the framework. For now, we have gradient echo, spin echo, 2D and 3D, all weighted in diffusions. We also have an EPI sequence, 2D and 3D, and we're working on an EVI sequence. Or you can modify the code to create your own sequence if you want, and then compile them. Once it is compiled, you will need to charge the DLL and SO files in your console, and you will be ready to acquire images. The images are not reconstructed using ICE, but you can use it. But mainly, you will need to retrieve the data from Twix and use Gadgetron as a reconstructor, as the framework is optimized for Gadgetron. You must note that Gadgetron implements online reconstruction if you want to use it. In order to test our framework, we built basic sequences like gradient echo and spin echo 2D and 3D and tested them on an ex vivo Nyala brain. If you want to know, a Nyala is a kind of antelope. And we thought that this ex vivo brain should be a good sample to test the sequences. As you can see on this example, if you want to build a gradient echo 2D sequence, you may need the preparation module like fat saturation shown here, and then a single TX excitation 2D module, a single line reading 2D module, a spoiling 2D module, and an end module. All the sequences are presented this way in the next slides. We also tested more elaborated sequences, like a spin echo 3D EPI sequence, as shown here, giving us some results. That is a little shared because we did not use either partial Fourier or Grappa, and we need them to have better images on postmortem materials with EPI sequence, and it is still a work in progress. But still, we managed to obtain also diffusion-weighted images featuring a nice fractional anisotropy map showing the main tracks of the brain. We wanted to have full access to the sequence module code so that anybody can modify them any deeper that they want. And we wanted an object-oriented architecture with clear variable names that is very readable for people who don't really know the framework, so that it is easy to handle. And we had to choose a first device. So we used Siemens, and since we added, we used it on IDEA VE11C, but the framework should be compatible with later versions, which are very close to this one. And we built, using the Siemens development kit, a hierarchical decomposition of any pull sequence, allowing you to build any sequence using only the timings. And we made it compatible with open source reconstruction using Gadgetron, so that the whole framework is open source and everything is available online following this link or flashing this QR code. So feel free to flash the QR code if you want. As a conclusion, we built an MRI pulse sequence development framework that is for now compatible with only one manufacturer. And we verified its pertinence on image from post-mortem Nyala brain and phantoms. We obtained a clear architecture with readable variable names so that people have an easy time implementing the framework, and it enables basic, diffusion, and rapid imaging sequences. As future work, we would like to develop Ginkgo for other vendors like GE, Philips, or Canon, which will be very nice for the community. And we would like to cover a broad range of diffusion MRI schemes and test them with human volunteers. We will soon provide an online documentation to help you handle the framework, and any contribution from the community will be very, very welcome. I would like to thank my supervisors, Cyril and Philippe, and all my team for helping me in that work. Thank you very much for your attention. Do you have any questions?